Welcome, everybody. It's nice to see you all here this evening. My name is Rowan Fladd. I'm a professor of anthropological archaeology here at Harvard, and I'm standing in for Jeff Quilter, who is unable to join us tonight. The director of the Peabody Museum is on his flight back from England, and he sends his regrets. But he's happy to see you all here with us. I'm happy to see you all here with us for this latest installment in the Divination lecture series that the Peabody Museum has been running over the course of this academic year. Tonight we're going to have scientist and author David Orrell talk to us about the history and challenges of prediction from the oracle at Delphi up to the latest methods being developed in areas like systems biology and economics. I wanted to welcome you all to join us after the talk up on the third floor of the Peabody Museum for a reception where we'll be able to converse with our speaker a little bit more casually. We also have immediately to my right a table where several books that David has authored are available for purchase and for signing. We also have on that table a list of events that are going on at the Peabody Museum for the rest of this academic year. In case you don't want to pick up a paper copy, we also will be able to provide you information online if you provide an email address to us. So please do stop by if you want to get more announcements about our series. David Orrell is an acclaimed writer and mathematician visiting us from his current hometown of Toronto. He has gained wide recognition and attention for his writing and research on the topic of prediction and forecasting, making him a perfect addition to the museum's year-long series on divination that began almost 10 months ago now with a talk on Chinese divination systems from the Bronze Age. He studied mathematics at the University of Alberta before moving to Oxford, where he received his doctorate in prediction and nonlinear systems. And then he worked subsequently in applied mathematics, which has taken him into diverse areas, including particle accelerated design, weather forecasting, economics, and cancer biology. His books have been translated into over 10 languages and have appeared on the local and national bestseller lists. His recent book, Economyths, 10 Ways Economists Get It Wrong, and I'm sure there are more than 10, was a finalist for the 2011 National Business Book Award. Apollo's Arrow, The Science of Prediction and the Future of Everything, was a national bestseller and finalist for the 2007 Canadian Science Writers Award. That particular book is available along with David's book, Truth or Beauty, over on the table, as I mentioned. David also writes for numerous publications, including World Finance, Adbusters, the Literary Review of Canada, and his work has been featured in places such as New Scientist, the Financial Times, and the CBC TV. He continues to conduct research in the areas of systems biology and economics, and also runs a mathematical consulting firm, Systems Forecasting. Today he's here to talk us about the topic, Perfect Model, the Past, Present, and Future of Prediction. Please join me in welcoming David Orrell.
Thanks very much for the introduction, and thanks to the organizers for inviting me here to take part in this series on divination. Yeah, I think our interest in divination and looking into the future is tied up in many ways with our desire for a world which is comprehensible and sort of stable in a way. And just allow me to say how shocked and saddened I was by these events at the marathon recently. I think it's things like that which make the world seem exactly the opposite of stable and comprehensible. So we have this desire to look into the future to make sense of the world, and I think it was well captured by the hockey player Wayne Gretzky. He says, a good player plays where the puck is, a great player plays where the puck is going to be. And this sort of captures the idea that we want to look into the future, see what's coming around the corner so that we can position ourselves better for it. There is actually a caveat, which is that this technique only works if not everybody does it at the same time, because otherwise the referee would drop the puck and everyone would skate away from it to where they thought it was going to be at some point in the future. And that turns out to be important, so I'll come back to that. But it's true. We want to look at the future. So if you're a student, you might be thinking, okay, what's the job market going to be like when you graduate, or If you're interested in stock markets, you might want to know what's going to be the next big business success, or maybe you're thinking longer term things about what's going to happen with climate change and so on. So we want to look into the future, but on the other hand, there's also this sort of countervailing fact, empirical observation attributed to Yogi Berra, among other people. Prediction is very difficult, especially about the future. So I'll give you 3 examples of that from the first one is to do with weather or climate change. So one of the sort of key questions about climate change is if the carbon dioxide levels in the atmosphere were sort of to double, what would the effect be on the climate? And the first conference to look into that was held back in '79. And at that time, there were only really 2 models. And so one day, the first model was presented and it gave a warming of 2 degrees. The next day, another model was presented. It gave a much higher warming of 4 degrees. And then at the end of the conference, they just sort of split the difference and added a fudge factor and came up with this range of 1.5 to 4.5 degrees centigrade, which is, so that's fine. What's strange, though, and is that over the intervening decades, that range, which is really quite large, 3 plus or minus 50%, has not got smaller. Really, it sort of changes a little bit, but basically it hasn't shrunk down. And actually, some studies suggest that the true uncertainty is probably even bigger than that. So this is curious. This is not what we're used to in science. I mean, normally in science, the harder you look at a problem, you get to finer and finer accuracy. But that doesn't seem to be happening here. Perhaps the most graphic example of our difficulty in predicting the future was the recent financial crisis, which was not the finest moment for the forecasting community. It wasn't just, people at Bloomberg.com failed to predict the crisis, but the same was true of big institutions like the IMF and OECD and Federal Reserve and so on. Then there's the area which I work in now, mostly biology. When the Human Genome Project gave us access to the Book of Life, it's turned out to be a bit of a puzzler because although this has completely changed all sorts of areas of the way that biology is done, the cost of developing successful drugs has actually soared, and it costs over $1 billion to develop a new drug. And we still can't predict the spread of pandemics like avian flu or swine flu. So what's going on here? Why is it that despite the resources we're putting into these things, we're not really getting much better at predicting the future? And are these problems related? And I think they are, and I think they're connected to our rather mechanistic way of thinking about the world. So I'm just going to start by giving a very kind of brief run through the history of prediction, our Western tradition of prediction, and then talk in a bit more detail about how we make predictions in these 3 areas. Okay, so our Western tradition of forecasting started with this person, the oracle at Delphi. And the Pythia acted as a channel for Apollo. So divination means inspired by God, and for the Pythia, the main requirement was enthusiasmos, which didn't mean enthusiasm. It meant actually being possessed by God, the god Apollo, the god of prediction. And the oracle would be consulted on everything from minor matters of health to major questions of state, like such as should you go to war. And she was a woman. She'd be sitting here on a 3-legged stool known as a tripod, and it's said that she inhaled vapors from a cleft in the mountain, perhaps ethylene gas, which put her into a kind of a trance. And her predictions were, perhaps as a result, were often kind of vague or even double-sided. But actually, perhaps for this reason, because it was hard to show that her predictions were actually false, this was the most successful forecasting operation in history. It lasted for almost 1,000 years. So one of her more accurate predictions, and her more famous predictions, was the birth of this guy, the philosopher Pythagoras, who was considered a demigod by the Greeks. And he was named after the Pythia, and he was believed to have been fathered by the god Apollo. And he would go on to found a school of prediction that was based on number. And actually, it amounted to a sort of what you might call a pseudo-religious cult, which was built around number. And the Pythagoreans are best known for their theorem about right triangles, but perhaps their most important insight was the discovery that music can be reduced in a way to numbers. So if the notes which harmonize well are related by simple mathematical relationships, equations. So if you take a string and you pluck it, you get a note, and if you fret it exactly halfway up and you pluck it, you get a note which is an octave higher. And then it turns out that all the notes which harmonize well are related by these neat mathematical ratios. So this was sort of a staggering discovery at the time, right? Because music was considered the most expressive and mysterious of art forms. So the idea that it could be reduced to number implied that perhaps everything, the universe itself, could be reduced to number. So the Pythagorean philosophy was summarized by this list of 10 opposites that I think it's interesting in a number of ways. It's a little bit like yin-yang, so the left-hand column with right, male, at rest, straight, and so on would correspond to yang, the right-hand column to yin. But there is an important difference, which is that the left column was sort of considered good, the right column evil. So basically the Pythagoreans try to align themselves with the qualities on the left-hand side. And so it was, instead of being seen as sort of two opposites that are connected, it was like polarizing them in a way. And it also spells out, some of these pairs spell out something which is a bit like a kind of an aesthetic code, if you like, for science. So for example, one versus plurality. This is the idea of unity, and scientists are always looking for unified theories which explain everything. Stability is at rest versus in motion. We'll see that a lot of our models are based on ideas of stability, as well as linearity, straight versus crooked. Light versus darkness. Light is associated with the light of reason, so rationality. And square versus oblong, this idea of symmetry, that something trying to make everything square and simple, as we'll see, also plays a very strong role in our predictive models. Okay, so as I said, music, because of their success at reducing music to number, they believed that the movements of the entire cosmos could be described similarly using number and the idea of harmony. And the Greeks developed a predictive model of the cosmos, and this was used primarily for astrology. And this was based on two assumptions, neither of which were right, but it didn't really matter. So the first one was that everything moved around the Earth, and the second was that everything moved in perfect circles. And the reason for choosing circles was really primarily aesthetic. As Ptolemy said, these circles are strangers to disparities or disorders. So this model worked very well in a sort of intuitive way for the stars and the sun and so on. But with planets, for some planets it posed a problem because they would go around and then stop and then apparently backtrack and then continue on their way. And so to get around this, rather than ditch the circle idea, they just added more circles. So this is the idea of epicycles, a smaller circle which moves around a larger circle. So this model was, it became the official model of the church, and it remained unquestioned for centuries, right up until the Renaissance. So why was it so successful? Well, the main reason was that it worked. It could predict things like eclipses to a very high degree of accuracy. And when you think about this was a time when what happened here on Earth was believed to be affected and influenced by what was going on in the cosmos. This was a staggering demonstration of the power of mathematics. So the geocentric model, as I said, it became adopted by the church, and it was believed that the planets, the celestial bodies played different notes. So stars would play D, Saturn would play the notes C, Jupiter G, and so on. And the result was a kind of a harmony, what the Pythagoreans called the harmony of the spheres, which is a sort of beautiful celestial music. And this idea that the the cosmos was based on this sort of this beautiful numerical order and harmony, also implied that human beings should try to align themselves with that. And so the Roman architect Vitruvius said, without symmetry and proportion, there can be no principles in the design of any temple. And so for this reason, buildings were built using around the ideas of symmetry and circles and squares. And here, Vitruvius actually tries to force the human body to fit into the circle and the square. You notice that the limbs are rather distended there. And his influence can be seen in buildings such as the Pantheon in Rome, with its geometrical proportions, its motifs of circles and squares. And later this got picked up again in the Renaissance by architects such as Palladio in Italy and Inigo Jones in England. Similar interest in this kind of classical geometry also infused other areas such as art. So in the early Renaissance, the Baptism of Christ by Pier della Francesca, the square represents the earthly realm and the circle represents the heavenly realm. And then with Leonardo da Vinci, something interesting happened here, which is that in his version of Vitruvian Man, you notice that the circle and the square are no longer in perfect alignment anymore. So it's like he's shifted them. He's broken symmetry. And the reason is that he was basing his paintings on close observation of human beings and of the natural world, and he just realized that actually, if you just shifted it slightly, it gave a much better result. And of course, this has gone on to become an iconic image. And I think this sort of prefigured what happened in science in a way, because those two key assumptions of the Greek model both came under question in the same way. So Copernicus proposed that Earth went around the sun rather than vice versa, and then Kepler showed that the orbits were not circles but actually ellipses. And he didn't actually like that very much because in his earlier work, he believed that they were all circles that were kind of stacked together based on the perfect solids of Pythagoras. But he realized that ellipses actually gave a much better fit. And then Isaac Newton came along, and he derived his three laws of motion and the law of gravity. And so this was interesting because like Kepler had shown that the orbits aren't circular, they're elliptical. But Newton showed that underlying that apparent sort of asymmetry is a law which is very elegant and symmetric according to all these principles. So this is the equation here. And basically it says it's symmetric. So for example, if the Earth attracts the moon, but the moon also attracts the Earth in return, which is why we have tides. Immutability, it doesn't change. The law of gravity is supposed to hold everywhere in the universe, subject to Einstein's adjustments, of course. Unification, this law can be used to describe the motion of the moon around the Earth or a falling apple. And elegance, it does all this in an amazingly compact and elegant form. There's only one unknown parameter here, the gravitational constant. And it's a very simple equation which can describe all of this huge range of phenomena. So Newton believed that matter was made up of these solid, massy, hard particles, i.e. atoms. And so this laid out a template which science has really continued to follow until the present day, which is that to understand and predict a system, you just need to break it down into its constituent parts, figure out the equations which govern them, and write them out as equations and solve. And so this is what we do. So in something like weather, we look at parcels of air and water vapor. In the economy, we look at individuals or firms. In health, we look at genes or proteins. And so this has been very successful, obviously, in areas such as physics and chemistry and so on. But how's it doing with these sorts of things, these things that we actually want to predict on kind of a daily basis? So to answer that, I'm going to look at each one of these three quickly in turn, starting with weather. So the term weather forecast was actually introduced by Robert Fitzroy. So he was the captain of Darwin's Beagle. He set up the first UK Met Office in 1850s, and he defined it as follows: prophecies or predictions they are not. The term forecast is strictly applicable to such an opinion as is the result of a scientific combination and calculations. You can see he's trying to be very sort of detached and objective and scientific here. And the reason was that he was kind of caught between sort of two different camps. There's, on the one hand, he was in competition with astrologers and people like Zadkiel's Almanac, who were coming, making all these flaky predictions. And then, on the other hand, there was the scientific establishment that was looking down on his attempts to make these prophecies, and these pressures actually probably played a role in Fitzroy taking his own life. But then during the First World War, the mathematician Lewis Fry Richardson, he was serving as an ambulanceman, and he managed to make the first numerical weather forecast. And he did this by taking some observations from weather balloons over Europe and dividing the atmosphere up into a number of into a grid, basically, and then using differential equations to solve how the equations of fluid flow for this region. And he managed to do all this while he was working as an ambulanceman. And so he was only trying to predict what would happen 6 hours ahead. So this is actually a hindcast, not a forecast, kind of looking at past data. All of these calculations took him six weeks to perform, and the results were actually way out. But it was sort of a proof of principle, if you like, that this kind of thing could be done. And he imagined this forecast factory full of computers who would be people with slide rules. And there would be each person would be responsible for a separate part of the globe, and then there would be this central figure directing, like a conductor of an orchestra. So Richardson's dream was eventually realized in the 1950s, but of course the computers were punch card machines like the US Army's ENIAC computer, and soon researchers were producing complicated 3D general circulation models, which are loosely based on the equations of fluid flow, sort of quasi-Newtonian equations. And much of this research was actually funded by the military, because of course weather has always played a very important part in military conflict, and there was a hope that they would not just be able to predict, but even control the weather and turn it into a kind of a weapon. But in since the 1950s, despite massive advances in computing, so computers today, the fastest ones are about 1 million times faster than ENIAC. Observational power, such as weather satellites, huge demand from industries such as agriculture. Weather forecasting has certainly improved a great deal, but it hasn't really improved as much as people thought it would back then. And predictions are good for a few days, certainly, but things like precipitation or especially extreme events are difficult to predict, and controlling the weather is right out. Although certain leaders have, I think Hugo Chavez in Venezuela claimed that he controlled the weather, and I think they tried to do it in North Korea or somewhere as well, I'm not sure. But anyway, but in general it remains elusive. So why is it the forecasts haven't improved more? Well, in the 1960s, this idea of the butterfly effect came out of MIT here down the road, and this I guess everyone is probably familiar with this theory. So the idea is that the weather is an incredibly sensitive system, so perturbing it slightly, such as something like a butterfly flapping its wings, can create a disturbance which sort of ripples out and can create a storm on the other side of the world. And so this became a popular, in the media, but also in the forecasting community, explanation for the inaccuracy of weather forecast. So actually, when I was working in this area back in the late 90s, it was sort of the default explanation for why forecast went wrong was the butterfly effect. And there was even this thing called the perfect model assumption, which sort of stuck in my mind. We will assume that our numerical model is essentially perfect because all the error must be due to chaos. So on the one hand, it was bad because it meant that we couldn't predict exactly what was going to happen, but if the model was correct, then you could still make these probabilistic forecasts. So instead of just running one forecast, you run lots of them. It's called ensemble forecasting, and then you can do sort of statistical stuff and make a probabilistic prediction. So it's a little bit like the Oracle of Delphi being a little bit kind of vague and, you know, making predictions which are a bit harder to validate. So, but when we looked at this, we came to the conclusion, I mean, I've always thought the butterfly effect is a little bit of a strange theory when you think about it, because, I mean, if you sort of, you know, flap your hand in front of your face, you don't really get the feeling that there's a disturbance rippling out from you, which is going to go and, you know, complicate the job of some Brazilian weather forecaster in 2 weeks' time on the other side of the world. What's more likely is that it's just going to dissipate rather quickly, you know, even if you're actually outside, not in a room like this. And, you know, we came to the conclusion that actually there's a much simpler explanation, if less attractive, which is just model error, which is, you know, the models cannot capture the full complexity of the atmospheric system. So, I think there are really two main problems when you try to build a model of one of these systems. So one is the idea of emergent properties. So that emergent properties, like local effects in complex systems, lead to emergent properties that by definition cannot be reduced to simple physical laws. So this tends to happen when you have sort of small local effects which grow and then create an effect at a larger scale, which you could not have predicted and without actually recreating the entire system in full. So an example of this is clouds, which are formed when water droplets locally cluster around small particles such as dust or salt or whatever in the atmosphere. And so this is all sort of local things. And there is no kind of shortcut way of doing this. There's no kind of simple equation that you can come up with. All we can do is kind of build models which capture the proximate amount of cloudiness which we will expect given certain atmospheric conditions and so on. But the formation and dissipation of clouds is one of the most challenging aspects of weather or climate forecasting. And the reason is that these sort of Newtonian equations, they just don't work when you get into that situation. The other problem is complex systems such as the atmosphere are dominated by opposing positive and negative feedback loops. So positive feedback, this is an example of this is clouds again. So heat increases water vapor due to evaporation. And then this increases cloud cover, which cools the atmosphere. So that's negative feedback on heat, except at night when it does the opposite because the heat is allowed to escape. So it actually heats the atmosphere. So that's a positive feedback effect. And these forces are in a delicate balance, which makes models sensitive to small changes. So there are similar problems when modeling and predicting other kinds of complex systems. And so in biological systems, for example, if you look at any kind of what's actually going on in a typical biological system in your own body or whatever, it's just kind of a morass of feedback loops. So for example, positive feedback loops allow a rapid response, something like blood clotting, for example, something that has to happen quickly. You have a lot of positive feedback driving it. And yet at the same time, these things are coupled with negative feedback that provides control. In the stock market, as we'll see, you get positive feedback from people like momentum buyers versus value investors who tend to act as negative feedback. So I think that the Greek philosopher Heraclitus, who was a contemporary of Pythagoras, put it best when he talked about this harmony of opposite tensions. There's this, so it means that apparent stability, right? It looks like there's nothing happen, but there's actually strong forces going on underneath. And that means that the situation can change suddenly and wildly, as in earthquakes, extreme weather or climate events, or something like financial crashes, which I'll come to next when we talk about economics. Okay, so in economics, the tools used for predicting the economy actually followed a rather similar path as what happened in meteorology. Our orthodox or neoclassical theory was developed in the 19th century. It was explicitly inspired by Newton's rational mechanics. But is the economy really like a machine? Or, do people behave like atoms? Well, Newton didn't think so, as he said. After he lost most of his fortune in the collapse of the South Sea bubble, which was the economic crisis of his time, I can calculate the motions of heavenly bodies, but not the madness of people. But economists, being eternal optimists, decided to press ahead anyway, and they came up with this theory, neoclassical economics. So here the atoms of the economy are individuals or firms, and they are assumed to act independently and rationally to maximize their own utility. This led to the idea of the rational economic man, and everybody knows that this is a caricature and no one really believes it's completely true, but it has been a very influential caricature. It's kind of the epitome of Nietzsche's Apollonian principle of individuation, where it's basically just kind of shrinking everything down to the needs of the self. And then the idea is that the actions of all of these self-interested individuals through the invisible hand drives the economy to a stable equilibrium, and the result of all this is supposed to be maximum societal happiness. And these assumptions were used to build general equilibrium models, right, just as with weather models. But if you look at the equations for general equilibrium models, they talk about these flows and equilibrium conditions, and sort of the same idea that you have with a weather model, but instead of flows of air or water, it's flows of money. But it's turned out to be even harder to predict the economy than it is to predict the weather. The graph here shows the solid line is changes in gross domestic product in the United States year to year, and predictions are the lighter lines from the Energy Information Administration. And really, these kinds of predictions are not much better than just making a kind of a naive forecast, which would be to sort of take the average of the last few years or just do something very simple. And this isn't just the case for the EIA, it's the same for other forecasters as well, such as IMF and so on. So, very difficult to do. And then in the 1960s, again, sort of as with chaos theory, as with the butterfly effect, the efficient market hypothesis became a popular explanation for the inaccuracy of economic forecasts. So this is a physics-inspired theory, and it assumes that, basically it assumes that the price system is perfect. Okay, so changes are due to random news. So for that reason, because they're random, they can't be predicted in any way. So it's sort of a physics-inspired theory where you think of something that's completely stable and it's just getting randomly perturbed every now and then. And so prices are perfect and they instantaneously adjust. And there are different versions of the efficient market hypothesis, but that's, the basic idea is that the system is magically self-correcting. And again, rather like the butterfly effect, which is putting these rather magical properties onto the atmosphere, here the efficient market hypothesis is putting rather magical properties onto the economy. Because if anyone who works in engineering knows that it's very difficult to build any kind of a system that self-corrects all the time, is always perfectly stable and can handle any perturbation. So this is rather a remarkable property that we're ascribing to the economy here. So the market cannot be predicted, but as with the weather forecasting, it is possible to make probabilistic predictions. Okay, so the idea is that you can calculate risk based on the normal distribution or variance thereof, the bell curve. And the normal distribution has similar mathematical properties as a square, normal being from the Latin for square, or the circle, in that the risk of something can be reduced to a single number. So basically what you do is you look at, let's say, an asset like a stock, fluctuation, price up and down, and then by looking at how much it has fluctuated over a certain time period, you can ascribe a standard deviation to that, and that is one number which tells you how risky that asset is in theory. And this technique formed what Alan Greenspan called an intellectual edifice, which included all sorts of things like Black-Scholes, Gaussian copula, value at risk, all these sort of risk formulas, which were kind of based on versions of this. And this all collapsed during the recent financial crisis, when it turned out that these risk models just simply did not work. They grossly underestimated the chance of extreme events. So why is this? I mean, one theory, which Greenspan mentioned after this quote, is that they just weren't trained on enough data, that they were trained when you were looking at these fluctuations, that you were just looking over a period when everything had been kind of calm and nice and positive, and that was the problem. But could it be that actually the problem is much deeper than that, and goes right to, you know, the core of the way that we think, these sort of Apollonian assumptions, if you like, that we're putting into our forecasting models? So just go through some of these sort of gold-plated ideas, such as stability, symmetry, and rationality, and so on, that we find all the time. So stability, first of all. Our theory assumes that the invisible hand drives the economy to a stable equilibrium, but is the market ever stable? I mean, if you just look at something like the price of gold, which has been in the news recently because it was falling so quickly, and I mean, it was certainly stable, obviously, up until the late 60s because it was being controlled by the government, but then when it was released to market forces, the invisible hand here seems to have a bad case of the shakes because it's wobbling around all over the place, right? And this is something that makes sense from when you think about it from, if you sort of forget about the idea of stability, because stability is actually a very special property of the system. As I said, it's not easy to get stability, and it tends to be something that's produced by negative feedback. But in something like an asset such as gold, positive feedback is incredibly important, because if you think about something like gold, the reason you're really buying it often is because it's a store of value, and when it's going up in value, you know, people get excited and they buy more, and that drives the price up further. So that's a positive feedback, and then you hit a kind of a tipping point, and the same thing happens on the way down, and you get this characteristic boom-bust behavior. And it's often sort of questioned whether the price of gold is in a bubble or not, you know, but it's not really the right question because it's always in a bubble, you know. The gold, there's no number which tells you how much gold is worth. There's no number written on it anywhere. It's what people think it is. It's just how much do humans value it for its beauty, but fundamentally for its store as wealth. And that's a psychological construct, a sociological construct. So so it's a bubble, which is, and I don't mean that to sort of imply that it's overvalued all the time, but it is more like a bubble, which is constantly deflating and inflating and deflating and so on. It's just going up and down. So this kind of boom-bust behavior is characteristic of not just of gold, which you could argue is doesn't sort of have a strong sense of integral value, but it's also true of the housing market, as is well known now, and even something like oil. I mean, oil is often called the lifeblood of the economy, but back in 2008, it looked like we were having a cardiac event with this massive spike. So this kind of, here again, the solid line is the oil price, and the dashed lines here are the forecast, again, from the Energy Information Administration. I'm not trying to pick on them. It's just that for forecasters, they do a good job of supplying data from their past forecast, which isn't always the case. But it is interesting to note that back in the early 80s, they were predicting a price spike, and I think this is probably a memory of the 1970s price shocks. And then as prices, when there wasn't, you know, the forecast sort of learned that wasn't going to happen, and got flatter and flatter and flatter until then there was this massive spike, and it plunged back down again. So, all right, so this kind of unpredictability of something like gold or something like oil is superficially consistent with the efficient market hypothesis, and it is frequently kind of trotted out as a sort of a proof, you know, that it must be true. But really, this isn't the case. I mean, the fact that something is unpredictable does not mean that it's efficient, right? I mean, you know, snowstorms are unpredictable, but no one says they're efficient. The risk calculations, which all of this is, which are the sort of efficient market hypothesis is used to make, they also assume that price variations are small, random, and independent, and therefore normally distributed. Or at least nearly normally distributed. But it turns out that if you actually just look at the data, the price fluctuations follow a completely different sort of a distribution. And it's known as a scale-free power law distribution. And one implication of this is that large events can occur. Risks can be much bigger, as in September 2008 when it was nearly lights out for the entire economy. There's this quote from Goldman Sachs around that period. We were seeing things that were 25 standard deviation moves several days in a row. Well, a 25 standard deviation move is something that should not happen once in the lifetime of the universe. So if that's happening several days in a row, then you know there's something wrong with the modeling approach. And okay, so what is the scale-free power law distribution? Well, a good way to see that is on the surface of the moon. They don't have financial crashes there, but they do have craters, and it turns out that they follow exactly the same kind of distribution. So if you just imagine that each one of these craters is a price, some sort of price shock, in the stock market, what you notice is that it's very asymmetrical. So most price changes are small, but there's a number of bigger ones, and then there's the possibility of this absolutely huge one in the middle. Scale-free refers to the fact that there is no natural scale. There's no sort of, it doesn't really make sense to talk about an average crater size. It's not a meaningless concept. In the normal distribution, or whatever we think about what's normally expected, but what is the normal crater? I don't know. I mean, and you can't get it, for that reason, when you look at it, you can't get a handle on how big this is. I mean, how big are these craters? How big is that one in the middle? It could be, what's the unit? And the only way you can do that is by overlaying something, in this case Europe, and then you can see that the big crater in the middle is actually the size of England. Right? So that would be the Great Depression of earthquakes. I mean, and the thing is that extreme events are part of the landscapes. They're not, these things which seem like financial crashes which come out of nowhere are not aberrations. They're actually part of the system. Another system which shows this sort of power law statistics are earthquakes. So most earthquakes, there's always sort of small tremors going on which are undetected, and then a smaller number of earthquakes which you can actually feel, and then again a very small number of extreme events. The similarity with financial crashes goes even deeper. The left plot there shows fluctuations in the S&P 500 around the financial crash. One Lehman's employee said it was like a massive earthquake. And this is the vertical, the acceleration and the ground shocks during the Kobe earthquake. So you can see that there's quite a degree of similarity. So back to these assumptions. The theory assumes that the people act independently and make rational decisions to optimize their own utility. The proof of market equilibrium actually assumes infinite computational capacity. And then there's rational expectations theory, which has been hugely influential. So it's a bit like we're modeling ourselves as if we're like the all-seeing eye, which adorns the back of every US dollar bill. There's a sort of amazing power to understand the future. But of course, the truth is a bit more like this, right? That as we know, as behavioral economists and other people have been pointing out, we're influenced in our decisions by trust, by confidence, by fear, by emotions of all kind. And we're trying to fit this kind of thing with our circles and our squares, but it's not really working. Neoclassical theory was really based on the idea, and it was a very noble cause actually, because the idea was to optimize happiness, and it assumed that the economy would realize the maximum energy of pleasure, the divine love of the universe. But what we've seen from the data, is that the gross domestic product in the United States, for example, in rich countries in general, has increased greatly in recent decades, but reported happiness levels and happiness levels measured in various ways show that happiness actually has been fairly static or even slightly declining over that period. And there are some reasons which are put forward for that. And one reason which is certainly plays a role is there's kind of a saturation effect, right? Which is that when you make once you've made above a certain amount of money, then you get a limited extra pleasure from getting more than that. But maybe there's another thing as well, which is that we've perhaps internalized some of the aspects of this economic model, all the stuff about maximizing our utility and being rational and selfish in our decisions, when in fact we know that what makes you happy is often stuff to do with community and doing things for other people. It's often the case that it can make you happier to buy something for somebody else than to buy it for yourself, and so on. And so it could be that actually this theory of ours is making us unhappy. You know, we're not very good at predicting how to make ourselves happy. Just as with as individuals are treated as being completely rational, the economy is believed to be governed by rational objective laws, but this doesn't take into account what George Soros called this reflexivity of the economy, which is that I'll give you some examples. There's this quote from Douglas Adams, the British humorist: "There is a theory which states that if ever anybody discovers exactly what the universe is for and why it is here, it will instantly disappear and be replaced by something even more bizarre and inexplicable. There is another theory which states that this has already happened." So the laws of physics are obviously not reflexive. I mean, when Newton discovered the law of gravity, it didn't change just to annoy him. But the economy is. Economic models change the economy. So as an example, risk models drastically underestimate the chances of extreme events. This makes banks take on more risk, and this makes extreme events more likely. So the models are affecting the reality. Banks use the same models, so when volatility exceeds a threshold, they all give a sell signal at the same time. Right? So this goes back to the Gretzky quote. Methods only work if not everyone uses them at the same time. Someone needs to play the puck where it is. Because we think the economy is stable and self-regulating, regulators relax the rules, and this makes the economy even more unstable. So the main problem with these our mathematical models of the economy is not that they failed to predict the crisis, is that they actually helped to make it happen. Okay, so just to sort of summarize a bit here. So our orthodox theory and forecasting tools are based on these gold-plated ideas of stability, symmetry, order, and logic, which go back to the ancient Greeks. We model people as if they were rational, can see the future. We model the economy as if it obeyed the harmony of the spheres. You can almost hear the celestial music playing in the background. But it's far more wild than that. I think you can say the same about something like the climate system as well. It's much more wild than our models allow for. And I feel that we're doing the same thing that the Greeks were doing. We're imposing our ideas of order and stability and rationality onto the universe. But there is one difference, which is that the Greeks could predict when the lights were going to go out, right? You know, we can't do that. Our models don't have that degree of empirical validity. So what do we do? Normally in science, when science is working well, it proceeds by changing a theory only if another theory comes along that makes better predictions. But there's a problem. What if the system is inherently unpredictable? What happens then? And I think this is one reason why we end up with things such as the butterfly effect or efficient market hypothesis or theorems like this, because they explain away the unpredictability while retaining the power of the model. Right? So they're not really questioning the model's ability to make probabilistic forecasts, for example. So, but to move beyond that, so do we need another Newton or just a new aesthetic? Paul Krugman said, "The economics profession went astray because economists as a group mistook beauty, clad in impressive-looking mathematics, for truth." And I think the same could be said for other branches of science as well. There's something to be learned from that. So I'm going to talk now a bit about predictions, how ideas are coming from areas in the life sciences, and how these techniques, I think, can be useful for other areas as well. And there's a shift in perspective from seeing the world as a machine to seeing the world as a living organism. So are the differences? Complex organic systems, from a living cell to a society to the Earth's atmosphere, are characterized by these emergent properties, which emerge from local effects and cannot be reduced to simple equations. So examples are things such as clouds, social behavior. Systems operate at a state, not from stability or equilibrium, but a state that is better described as far from equilibrium, in the sense that the contents are constantly being churned around. This power law statistics are kind of the signature of systems that are operating far from equilibrium, which is the sort of statistics which are exhibited here. Network dynamics as opposed to individualistic atomic dynamics. And then there are these opposing positive and negative feedback loops, which create an internal dynamic tension. And all of this results in an inherent uncertainty, so that mechanistic models which attempt to capture these effects tend to be highly unstable and sensitive to small changes. And this is what we see with things like climate models or biological models or financial models as well. So a number of new mathematical techniques that are newish, they've been around for a while now, have been developed to visualize, understand, in some cases, predict these sorts of systems. So examples are network theory, nonlinear dynamics, agent-based models, and I'll give a couple of examples of these, and then also insights from other areas. So this is an example of what we can learn by studying networks. So this is a protein-protein interaction network for genes related to different diseases, and this is by a team of systems biologists. And the nodes here represent proteins, and lines represent interactions, which means that these proteins interact somehow to form a complex, or one regulates the other, or whatever. And the color coding here indicates the disease which these proteins play a role in. And then you can use this kind of visualization technique to zero in on how diseases might be related, as well as what proteins might be a promising target for a drug. Here's the same technique applied in a rather different context, the world economic system, financial system. So here, this is a network of 43,000 transnational companies, and here the nodes represent companies, and the lines represent direct or indirect ownership links. So this is sort of a snapshot of the power structure of the economy. And so this is quite revealing in a lot of ways. So for example, it shows that the power structure is very asymmetric. The top 1% controls over 40% of the power in the system. This is related to the fact that power law statistics, the connectivity of these nodes, a small number are very highly connected, while most have very few connections. Network effects means the network is very highly connected, and normally you might think this is a good thing, because it means that communication is made easy. But it can actually lead to problems such as contagion. So it means that a financial disturbance in one part of the world can quickly ripple around and affect the rest. In fact, this data was done shortly before Lehman's went bust, and Lehman's was in sort of ranked maybe 20-something, can't remember. And it just shows how fragile, how susceptible the system was to one of these nodes being knocked out. And in nature, in ecosystems, for example, tend to be built up of smaller subnetworks, which are kind of less closely networked. It's a dynamic system. It's changing all the time. So if you look at over the last 20, 30 years, the degree of connectivity has increased greatly. And there's a high degree of instability here, and this is as shown by the Lehman's incident. But the other thing that's kind of built into this is that if you look at the top companies, which are down here, most of them, I think Barclays, I think, was one, and most of the others are banks or something in the financial sector. And so these are all operating really in what you call the virtual economies. They're not sort of normal companies that are making or selling stuff. They're companies which are doing things with money. So they're creating credit. They're dealing in fancy financial derivatives, or credit default swaps, or things like this. And all of this is inherently unstable, because it's fine basically when the economy is going up and everything's going wonderfully, everyone's making lots of money. But then when things start to go badly, the problem is everyone wants to cash in their virtual chips at the same time, and that leads to a crash. So how do you, sort of back to the idea of prediction, how can we make predictions about these things? And I mean, just some, I think perhaps one of the kind of main insights is that prediction and modeling are not the same thing. So normally the way we go about predicting a complex system is just to build, sort of be very logical about it and reduce it to its parts and include absolutely everything in the model. And if something isn't included, then someone will point that out and you have to put it back in, and you end up with a very large, cumbersome model of the system, be it of a climate or biological system or whatever. But what happens in practice is that these models, they become more complicated. The number of unknown parameters, the number of things that you're basically just guessing increases. And then there's also the fact that you start to get all of these, as you become more realistic, you start to include all of these nonlinear feedback loops, which are very, very hard in practice to get right and make the model very, very unstable and sensitive to small changes. And empirically, there have been studies such as this M3 competition, but it seems to hold quite generally, is that simple models tend to be better at prediction. Perhaps just because if you have a very complicated model, you can always fit whatever historical data you want, but they're not very good at prediction. A simple model will do a less good job at predicting what happened in the past, but tends to be more robust and reliable for making predictions. And so the idea is to make what Arnold Zellner calls sophisticatedly simple models. This is an example of an agent-based model, and it's from a company that I work with, and it's a representation of a tumor. And so each of these circles represents cells, a cluster of cells, and then what you do is you follow these cells as they grow and divide and die, and then you get kind of an emergent behavior which captures reasonably well what happens in a tumor. But the model at the level of the individual cells is kept deliberately simple, really as much is left out as possible, in order to keep the number of parameters simple, in order reduced, so that you can actually fit this thing to the data. But while prediction is possible for some systems, in a way it's almost a question of there are pockets of predictability. There are things which are predictable. But we also need to acknowledge the uncertainty of living systems, and I think the medical analogy is appropriate here. So doctors routinely use their experience to make statements about health, but they generally avoid making precise predictions like, you are going to have a heart attack in exactly 37 days or something like that. And I think in the same way, we can use models and data to improve system health. I mean, the main problem with the world is not that it's unpredictable, but that it's very unstable, as shown by these things like oil price shocks and credit crunches and so on. And I guess the main question is, if we can't predict something like an economic crisis, how are we going to do it predicting an environmental crisis? So can we predict the exact timing or of the next crisis or opportunity? No. Can we use available tools to prepare ourselves better for it? Yes, I think so. And one way to do that is to compare these different systems and see what you can learn that way. So if you were to ask which of these is better regulated, well, the financial system is obviously not terribly well regulated. Human cells are normally amongst the most regulated of systems. They're regulated for absolutely everything. This is actually a prostate cancer cell, which has escaped regulation and therefore has become a threat. And then there's the biosphere, which has been around for a couple of billion years, although we are now starting to perturb that ourselves. And so we can learn a lot from that. Okay, just to summarize quickly. So our mental models in art or science shape the way we experience reality and therefore shape the world we live in. The Greeks believed that the cosmos was ruled by mathematical harmonies, and for centuries this was reflected in their art and architecture, and so there are these ideas of unity, stability, linearity, rationality, symmetry. In the Renaissance there was a shift towards realism, perspective, and objectivity, and this helped pave the way for today's scientific models. However, many of these sort of classical ideals were retained. And today, I think we are finding that this reductionist approach does have its limitations, and a new approach to modeling is emerging, which views the world more as a living organism than a machine, And this is coupled with a new aesthetics, which finds beauty in the complexity of life rather than the elegance of symmetry and geometry. So I think it's going to be more Frank Gehry than Mies van der Rohe on that one. Okay. Thanks very much.